Okay, I'm out of the car. I'm back home, and we stopped with chapter 2 with the, we did all the brain parts. Now we got to do the parts of neuron. I thought it'd be easier if I just pointed things out on here on the screen as we go along. Actually, I could probably type it in, but not one-handed very well. So number 13 is, what is a neuron up here? Well, a neuron is a nerve cell. A bunch of these put together make up a nerve. It's also brain cells. It's the communication cells of the nervous system. So the brain is part of the nervous system. It's a neuron, not a neutron. So when you're burning your brain cells with the drugs, you're burning neurons. That's the formal word. This whole thing is a neuron. We have these branches right here. Those are dendrites right there, dendrite, okay? They are coming off this big, large part called the soma or cell body, okay? That's the soma. That's the nucleus, so it's just showing you that. But that's like the main part of the neuron. Then there's this long string inside here. Now, I know it has these beads on it, but inside the beads, this is actually a long string coming off the soma. That long string inside there is called the axon, A-X-O-N, okay? It moves information away from the neuron. It's sending it to the next cell, right? At the end of the axon, it branches off into these terminal branches. Terminal branches, okay? It branches off like a split end of your hair. This allows the one message being sent along this neuron to go to many other cells at once. All these endpoints are communication spots for other cells. Now, some axons have these link sausages kind of thing on top of them, beads. There, it's called the myelin sheath, okay? So not all of those axons have a myelin sheath. Myelin sheath is like a fatty covering. The purpose of it, which is, I don't have a touch screen, which is a question number 16. So we'll jump down to question number 16. What are two functions of the myelin sheath? It is to protect and to speed up the transmission of information. So it protects the axon from any outside interference, and it speeds it up. Number 17, are all axons myelinated? Nope. Now, our diagram shows one that's myelinated. And if you go online and type in neuron images, Google images, you will find lots of them that have that myelin sheath, but not all of them do. So are all axons myelinated? No. How does the brain determine which ones to myelinate? Okay, so that's number 18. I'm just going to keep it here for now and not show you me, because we're going to do this diagram and then I'll turn it back on me. Let's see. How does the brain determine? It determines based on importance. It is going to myelinate what it thinks are the most important axons. Now the question is, how does it determine importance? It determines importance based on frequency of use. The more you use that neuron, the more that axon transmits information, the more important your brain decides it is. So it wants it to work quickly and be protected because it's important. So it will myelinate those axons. It is an active process. It decides this on a regular basis. You have axons being myelinated, okay, on a daily basis. This is, part of how the brain is changing all the time based on what we ask of it to do. All right. Back up to that diagram because we have one more part that we had to identify. Oops. Okay. The axon coming down along, branches out in the terminal branches. At the end of these terminal branches are something called terminal synaptic knobs. You guys, I guess your book calls it synaptic knobs. Sometimes they're called terminal buttons, end bulbs. They have different names. Remember, it can be frustrating, but I want to keep it what your book calls it, synaptic knobs. So that's what is at the end of each one of these branches. Okay, you can't see it very well in this diagram, but if you go down to number 15, then you can see it better. Okay, this is like a blown up version. This is a terminal branch coming down, and it just blows out at the end. Okay, it just elongates, it just bubbles out at the end. This whole thing right here is called the synaptic knob, according to your book. Okay, you see these little bubbles inside the synaptic knob? Okay, now we're labeling this part, number 18. Those are called synaptic vesicles. A vesicle is a container. It contains something. Anything to do with this area, and what this is a picture of is this is the end of one neuron and this is the beginning of the next neuron. Okay? Anything to do with that communication point between two neurons is called the synapse. So it'll have the word synaptic in there. You should be able to easily find videos about this showing how it works and pictures and stuff online. I think I have some links. Synaptic vesicles. Inside these bubbles, these synaptic vesicles, are little teeny dots, and those are neurotransmitters. They're the chemicals you hear so much about with people that have a chemical imbalance. So the chemicals live inside the synaptic vesicles that live inside the synaptic knob. Okay? Now, no two neurons touch. There's always a gap. This gap has a name. It has different names. Your book calls that gap the synapse. I don't particularly like that, but that's what they call it. It's also called the synaptic gap or the synaptic cleft. But your book calls it synapse. Okay? It's a space between these two neurons. This right here is the beginning of the next neuron. Let's go back up to our diagram. Okay? So we're showing this right here blown up. What this part of the neuron is talking to is this part of the next neuron. Dendrites receive information into the cell. They're the gatherers of information. They're getting information from other cells. Okay? If it's the right kind of information and enough of it, it'll cause this neuron to start kicking out information. And it passes it on to all the cells it's touching or talking to, not touching, talking to. So it's like a chain, but ends up being a web because this one could have communication with all these points. These could all be different cells. All these points could be different cells. So it's getting information from all these points, and it's also spitting out information to all these points. So it's a web. All right. Now, back to our synaptic thingy. Okay? Synaptic knob, synaptic vesicles, neurotransmitters, synapse. This is the dendrite. We have receptor sites on the dendrite. The receptor sites are there to receive the neurotransmitters. The neurotransmitters live inside the synaptic knob, but when a message comes down the terminal branch, if it's strong enough, it will cause those synaptic vesicles to go to the bottom of the synaptic knob and open up and spit out their neurotransmitters. These neurotransmitters cross the synapse looking for their special receptor site. They can only fit into their specially made receptor site. Okay? So that's been the description of the neuron and its parts. So I think we got all the way through 18, and actually we described a little bit of 19 through 20. And I think I'm going to keep the camera off of me because it might be easier to see, to be able to, I think I just showed you, but it'll be easier to point out stuff to you, I think so. All right, number 19. What two processes are involved in transmission of information along the neuron from one neuron to the next? All right, let's go back up to the diagram of our neuron, okay? Information comes in the dendrite, passes along the soma, along the axon, and along each branch until it gets to the end, the synaptic knob, okay? The information goes into the dendrite chemically, but once it's in the dendrite, it changes the status of the neuron. The neuron's just hanging out, not doing anything. It's not being used. We call it resting. Okay? The information is passed along the neuron when it's excited electrically. Everybody always hears about the chemicals. But our nervous system works on electricity also. That is why if you get a shock, it will affect the functioning of your body because we work on electricity too. That's why they give you ECT, electroconvulsive shock treatment, to your brain to change how your neurons are working when medication doesn't do the job. All right, so the question number 19 was, what two processes are involved? So it's electrical and chemical. Okay. Then they ask, what are ions? Number 20. Ions, you can't see it here, but this neuron is bathed in fluid, and it contains fluid on the inside of it too, okay? You hear how we're like 75% water or something like that? There's fluid on the outside, fluid on the inside. On the outside, in this fluid, both inside and outside, are electrically charged particles, okay? Little particles that have an electrical charge inside and outside the neuron. When the neuron is not being used, it's called resting. And when it's resting, the ions on the outside are mainly positive. Okay, so they have a positive charge. So the outside of the neuron is positive. When it's resting, the ions on inside of the neuron are negative. So the inside has a negative charge. Well, these two would like to get together, the outside and the inside. When this dendrite receives a strong enough message from another cell, it will start doors along this neuron opening and shutting and letting in the positive ions from the outside and spits out some of the negatives from the inside. We'll talk about that in a minute. But ions are electrically charged particles. So that was question number 20. What are ions? Number 21. The charge on the outside of the neuron when it's resting is what? Positive. The charge on the inside of the neuron when it's resting is negative. Okay. 22. What happens when the ions when the neurotransmitter enters receptor sites? So again, back up here. We said information comes in the dendrites from other cells. Okay. That comes in through chemicals. Neurons talk to each other through chemicals. Okay. Chemicals jump across that synapse to talk to each other. So it receives a chemical message from other cells. If it's the right kind of chemical and enough of it, it will start a chain reaction in the neuron of the electrical process. It's kind of like a relay race. The chemical people have a short little lap in the relay race. Then the electrical people run a long time in the race till it gets to the very end. Then they hand off to the chemical people. The chemical people take 3 paces, drop it off to the next neuron, and the electrical process starts in that next neuron. All right? So let me see what question we were doing. Okay, what happens to the ions, number 22, when the neurotransmitter enters the receptor site? So when we say information enters the dendrite, it's entering the receptor sites along the dendrite, okay? The neurotransmitters from the chemicals from other cells enter the receptor sites that are all along the dendrite, all right? So when that enters, if it's enough of the right kind, it'll start an electrical process. What's really happening for this electrical process is these are pumps. I sometimes call them doors, but there are pumps all along the skin of the neuron, okay? All along the branches and everything. And these pumps actively keep the positives out and the negative ions in. Well, if the message comes in from these other cells and it's strong enough, it'll shut that pump down. And when that pump shuts down, in rush all these positive ions trying to get in, okay? And then the pump starts back up again because it doesn't like to be shut down. It's just temporarily stunned. The pump starts back up and then it kicks out those positives because it doesn't like to have positives inside the cell. Kicks them back out. Well, that happens at that pump, but then there's a pump over here and a pump over here. And inside this myelin sheath, there's a pump here, 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 all along the axon. When this pump temporarily shuts down and then kicks back on, this pump then shuts down and kicks back on. Then this one shuts down and kicks back on. Then this one shuts down and kicks back on. Shut down, kick 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 on. We used to think, because we didn't have the technology to slow it down. We used to think that it was like a fuse. Because that's how fast it moves. But then we got better at slowing it down and we saw it's open, shut, stop, start, stop, start, stop, start, stop, start, stop, start. I think of it like dominoes. You hit that first domino in the row. That's all you need to do is hit the first one. And then bam, 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 they fall down after that. You don't have to go back and keep knocking each one down. They automatically fall down. And they fall down sometimes if you set it up well so quickly, it looks like it's just moving. That's what happens with this. It moves so quickly. How quickly does it move? It can move 3 feet per second. That's super fast, especially considering some of these axons are like teeny tiny. And this is what's allowing us to speak and think and walk and all those kind of things. Zoom. All right, so that was question number 22. Question number 23, all or none principle of firing. So when this neuron's pumps shut down, start back up all along the axon, all along the terminal branches, we call it firing, okay? So the neuron is either resting or firing. Firing is when it's active. Resting is when it's not being used. There's no ions exchanging places, okay? So that's what firing means. But all or none means your neuron is either firing or resting. It's not firing a little bit, firing slowly. It's firing fast or not at all. And they use it like a gun, the gun idea. When you squeeze that trigger, no matter how slowly you squeeze that trigger, that bullet's coming out at the same rate. It's not going to come out slower if you squeeze the trigger slowly, okay? It's all or none, fast or off. If, like, you're having a strong pain on your skin, what's happening is that neuron is continuing to fire over and over and over and over and over and over and over again, okay? It's not firing faster, it's firing more frequently. So more intense stimulation makes the neuron fire more frequently, not faster or harder. It's either fast or it's nothing. So that's what 23 means. 24, information passes along the neuron electrically and between neurons chemically. So let's go back up here. We talked a lot about the electrical process. Pump shuts down, lets the positive in, then it kicks back on and kicks the positives out. Pump here shuts down, lets the positives right around there in, and then it turns back on and kicks them back out. Pump number 3 over here shuts down, lets the positives around it in, then starts back up and kicks them back out. Boom, 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 boom. Part of the reason that it moves fast, if it's myelinated, is because some of those pumps are shut down. So the only pump that can open is this one, and then this one, and then this one, and then this one, and this one in between. So instead of shut down startup, 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 da 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 da, it goes shut down startup, shut down startup, shut da 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 da. It moves faster. Okay. So anyway, shut down startup, all the way down these branches. When it gets to the end, it's like a relay race. The message changes. So let's go down to our terminal button. This is one of the hardest things the whole semester. So this is the terminal branch coming down at the end of the one neuron, and it's got the pump shutting down and kicking back on, shutting down, kicking back on, shutting down, kicking back on, all the way till it gets down here. When it gets down here, it stops. You can think of it as it shocks, it kicks, it hits, it punches, whatever, these vesicles. These vesicles are normally just hanging out in the neuron, minding their own business, not being used. But this electrical current comes down, brrr, boom, hits them. They rush to the bottom of the synaptic knob, they fuse with the bottom, they rip it open, and then out come the neurotransmitters. Okay, the neurotransmitters, those chemicals, come into that synapse, and they look for their special receptor site. Okay, we've already talked about that, but that's the end stage. So question number 24 was, information passes along the neuron electrically. That's the pumps shutting down and letting those positive ions in. And between neurons, between the two neurons, chemically. That's that synapse area. Okay? And last question, number 25. Can receptor sites accept different neurotransmitters? The answer is no. Each receptor site is made special for their own neurotransmitter. They cannot jump in each other's. Now, the medicine we take looks like certain neurotransmitters. If it's meant to work in the nervous system, it will look like those neurotransmitters. So they can go in and work in the receptor site. But other than that, nope. And the drugs we take, like cocaine, they go in and look like neurotransmitters. So they can go in and do the same job. But neurotransmitters themselves cannot fit into each other's. It's like a key in a keyhole. Okay? They can only accept their own neurotransmitter. All right. That's it for Chapter 2 Study Guide. Bye.